Okay, this video is looking at another example of a galvanic cell or electrochemical cell, and we're going to go over how we might write a comprehensive overview of this cell and explain the following points. So we're going to use oxidation reduction potentials, these are at the top of the screen here, to identify what is being reduced and what has been oxidized, and therefore write reduction and oxidation half equations. We're going to link any observations that we see to the oxidation reduction reactions that are happening. We're going to justify which species are being oxidized or reduced. So we're going to say the reason that these are being oxidized and reduced is because they've lost or gained electrons, and we're going to be specific and detailed about that. We're going to also justify using oxidation states or oxidation numbers. Fifthly, we're going to go over balancing the half equations and then combining the two half equations, reduction oxidation one half equations, into a fully balanced equation. The sixth thing we're going to do, we're going to calculate what is the cell potential that this cell could potentially produce, and then we're going to explain any links, what this means in the wider world. Okay, just have a quick look. This is a galvanic cell. There are two half cells, one on the right, one on the left. They are connected by a wire through a voltmeter and a salt bridge between the two solutions. The salt bridge is there to make sure that their current continues to flow. Okay, it's to balance the charge. In the bottom, in the left solution, we have a magnesium electrode and we have magnesium ions. And on the right, we have an inert carbon electrode. That's an electrode that won't react with the solution. And in the solution, we have both Fe3+ and Fe2+ ions. It's important to note here that Fe3+ is a rust orange color. Fe2+ is a really faint green color. Magnesium metal is a gray color. Okay, let's see if we can write our overview of this. Okay, so let's see if we can go through and write our comprehensive explanation. The first thing that I'm going to do here is I'm going to look at this equation. I'm going to look at the reduction potentials at the top here, and I'm going to work out which one of these two is going to be reduced and which one is going to be oxidized. And it's quite simple. They each have a voltage attached to them, and the one with the most positive voltage is written as it is in the couple. That is, will be written in the equation. So if you can see here that Fe3+ Fe2+ has a voltage of plus 0.77 volts, that one there is going to go forward because it is more positive than the magnesium ion magnesium couple. So I'm going to write this redox couple as an equation. The forward slash is, we replace that with an arrow and we balance it with adding an electron. So we're going to get this charge here. Okay, so remember, because it's the most positive, it goes forward. Fe3+ has an electron added to it so that both sides have a +2 charge and it is balanced. Okay, now, so what I'm going to do is I'm going to justify whether this is a reduction based on its loss or gain of electrons. So reduction occurs in this equation as each Fe3+ gains one electron. Now I'm being specific and detailed here and saying that one Fe3+ ion gains one electron. To become Fe2+, I'm then going to link it to what I observe, okay, and that's really important. So I observe here that it becomes less orange, and this is because the concentration of the 3+ ions decreases, and iron 3+ ions have an orange color. So I've explained this and linked it to the observation. I've explained it using electrons, but you know what? The best way to explain it using oxidation number. So let's work out the oxidation number. Fe3+ is a monatomic ion, oxidation number +3. Fe2+ is also a monatomic ion, so its oxidation number is equal to its charge. We can see that the oxidation number has gone from +2 on the left-hand side, +3 on the left-hand side to +2 on the right. It is decreased across the reaction. This is reduction. Let's write this clearly. So the Fe3+ is reduced. This is because we always talk about the reactant, okay? So in this case, this is called an oxidant because it's getting reduced, but we don't need to say that. The Fe3+ is reduced as its oxidation number, as the oxidation number of the iron component, the iron atom that's in it, decreases from +3 when it's an Fe3+ to +2 when it's an Fe2+. Notice how I've said, I haven't just said it decreases, and I haven't just said it decreases from +2 to +3. I've said it decreases from +2 in Fe3+ to, sorry, +3 in Fe3+ to +2 in Fe2+. I've put all of that detail. And I need to make sure that I'm very specific about it isn't the Fe3+ that has its oxidation number reduced. It's the atom that's part of Fe3+ that has its oxidation number decreased. So I have to make sure I put that in. Okay, so our next equation, if the iron one went forwards, well, the other equation has to go backwards. One has to be reduced going forwards and one has to go backwards, which is being oxidized. That means we need to put magnesium on the left hand side and magnesium 2+ on the right, add electrons to balance the charge. Here we go. And there is our oxidation equation. Now, because this is oxidation, this must happen at the anode, right? Now, the reason oxidation always happens at anode, reduction always happens at the cathode. I always remember it because oxidation and anode both start with a vowel, with the R sound, and reduction and cathode both start with a consonant. Okay, so anyway, let's explain this using electrons. You can see that because there are electrons on the right hand side, the magnesium metal has lost 2 electrons. The mass of the electrode decreases as each magnesium solid is oxidized by 2 electrons. I'm being specific. 1 Mg solid is oxidized by losing 2 electrons to become the soluble Mg2+. This is why the mass decreases, right? So the mass decreases because the metal dissolves into the solution. That's why I've put the word soluble here. Let's see if we can work out the oxidation, explain oxidation using oxidation numbers. Magnesium has an oxidation number of 0 because it is an element, has no charge, and it's by itself. And magnesium is a monatomic ion, so it's +2. So we have an increase in the oxidation number, so we have oxidation, but we're going to write this detailed. The magnesium solid is oxidized as the oxidation number of the magnesium atom increases from 0 in magnesium to +2 in magnesium ion. Okay, so this first part here, I have drawn the 2 half equations. I have identified why I knew that the iron one was reduction, why it went forward, because it was more positive. I have explained oxidation and reduction, or justified it, explained it, both in the loss and gain of electrons and the change in oxidation number. I've also linked the observed color change to the reaction. So now what I'm left to do here is I need to write a balanced full equation. Let's go on to the next slide. Okay, so let's put our 2 half equations down that we had before. Here they are. And we want to balance them and turn them into a full equation. Now, when a reduction and oxidation equation interact with each other, they exchange electrons. And the number of electrons they exchange must be equal. So we must gain the same number of electrons in our iron equation as we lose in the magnesium equation. And to do that, this first iron equation that only has 1 electron has to be multiplied by 2. Everything inside this equation needs to be multiplied by 2. So I'm going to rewrite this equation out below. There it is, and everything has been multiplied by 2. So notice we now have we have the magnesium equation here, and then the iron equation with a 2 in front of everything. But the number of electrons in the iron equations, there are 2 gained, and in the magnesium there are 2 lost. So what we do with these is we cancel them out. So we can just add both of these equations into one full equation. Here we go. This is our fully balanced equation. And if we're doing the achievement standard 91393, we need this for one of our excellence points. Last thing that we need to do now is work out what the E cell, what the voltage produced from this galvanic cell. And we do that by subtracting the taking the right hand electrode and subtracting the left hand electrode. So we find the value for this, the iron value, and we minus the value on the left hand side, which is the magnesium. So E cell equals right hand electrode potential minus left hand electrode potential. We get positive 0.77 minus 2.37. And the answer we get is we get 3.14 volts. This cell, if I made a battery out of this cell, well, if I made it would be a cell out of this cell, not a battery. A cell is, anyway, it doesn't matter. It would be 3.14 volts. What does this mean in relation to if I was doing achievements that in 91393, I would have to say that, okay, what this means is that this cell will produce electrical energy. So it has a positive voltage. That means that the electrons will flow from left to right in this cell, left to right, and that this reaction, the reaction between these two things, will happen spontaneously and electrical energy is produced. So important I put the word down, spontaneous, and electrical energy is produced. And that's it. That's the comprehensive explanation of this galvanic cell. Hey, look out for my other video, which is one about a galvanic cell, another galvanic cell, and the new video about electrolysis and comprehensively explaining that. Good luck.